listening to Wurth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Wurth Elektronik specialists who are going to shine a light on our topics, like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast. Sensors are making huge advancements in today's technology, and now nearly all electronics have one sensor or another. Today, we are talking about the new WSEN-ISDS sensor from Wurth Elektronik. Now, the ISDS is a 6-axis MEMS inertial measurement unit, or IMU, and it includes system in package for both 3-axis accelerometer and 3-axis gyroscope. The module offers I2C and SPI serial interface communication, excellent accuracy, and ultra-flexible operations all in a tiny package. The sensor offers best-in-class high performance with low power consumption, which fits for many power-demanding IoT applications. Additionally, the WSEN-ISDS sensor incorporates 4 kilobyte FIFO data buffering for data storage with embedded smart function features like freefall, tilt, sleep and wake up, motion, and 6D or 4D orientation detection. Given its robustness to high mechanical shocks, WSEN-ISDS is well suited for a wide range of Industry 4.0 IoT applications. Now, this technology can be very exciting, but it's also confusing and could lead to further problems. In this podcast, we're going to discuss how well suited the sensor is for both static and dynamic motion sensing applications like localization, navigation, platform stabilization, connected devices, and robotics.
To start with today's agenda, the presentation is basically structured into 3 main parts. In the first part, we will mainly cover what is an IMU and what does it consist of. Well, this can be explained by using a simple block diagram and the working principles of both accelerometer and gyroscopes. Then we move on to the next part of the presentation, where we will discuss some key technical parameters, specifications, features, and characteristics of the ISDS sensor. In part 3, which is also the last part of the presentation, we will cover some IoT and industrial applications of the ISDS sensor. Finally, then we can conclude the webinar with some frequently asked questions. So in this slide, we will discuss what is an IMU. An IMU is an inertial measurement unit which consists of an accelerometer to measure the acceleration, gyroscope to measure the angular rates, and optionally sometimes it also includes magnetometer to measure the magnetic field surrounding an object. If one only considers an accelerometer in X, Y, and Z direction, it's called as a 3-axis IMU sensor, like our previously released WSEN-ISDS. And if one considers both accelerometer and gyroscope, 3 plus 3 axis, together in one single unit, it's called as a 6-axis IMU. To go even further, if one adds additional magnetometer to a 6-axis IMU, then it is considered to be as 9-axis IMU. In this slide, we will discuss the basics of an acceleration. By definition, acceleration is nothing but the measure of change in velocity. It's equal to the difference between initial and final velocities normalized with respect to a given time. A micro-electromechanical system, also known as MEMS, is a micro-machine structure built on top of a silicon wafer. An accelerometer's output signal is typically specified in plus or minus g, where g is the gravitation and is equal to 9.8 meters per second square. An accelerometer consists of a MEMS capacitive element inside the IC. In this slide, we will discuss the principle of acceleration. Let's assume a scenario that a mass m is attached to a spring with a spring constant k and is fixed to a rigid wall. Now let's assume the mass m is experiencing a force in the x direction as demonstrated in the figure. Then according to Hooke's law, the force F can be represented by spring constant times the linear displacement x. On the other hand, the same experiment can be interpreted with Newton's second law, that is force is mass times the acceleration. Equating the two equations for acceleration, we get acceleration is equal to spring constant normalized by the mass times the displacement x. This clearly demonstrates that the acceleration caused due to the force F on the mass is equal to the inverse of the displacement vector x. The key takeaway point from this slide is acceleration and linear displacements are correlated. So from the previous slide, it's clear that the acceleration measurement is possible by measuring the displacement. Now the real question is, how do we actually measure the displacement? We have different techniques to measure the displacement, like the resistive, inductive, and capacitive sensing techniques. However, our ISDS sensor is based on capacitive sensing technique and will be the main focus of this presentation. For the spring mass setup discussed earlier, if we set up two parallel plates, let's say PF being the fixed plate and PM being the movable plate. As shown in the figure, the displacement X can be measured by measuring the capacitance between the two plates. We know that the capacitance between the two plates is given by the formula capacitance C is equal to epsilon times the area normalized by the distance between the two plates. Here, the capital A being the area of the two plates. If we plug and reshuffle the previously derived acceleration formula, where acceleration is spring constant K normalized by the mass times the displacement, and the capacitance which is equal to epsilon times A by the distance between the two plates, we can establish a relationship between the capacitance, acceleration, and displacement. In this slide, we go deeper into the accelerometer sensor block diagram. Firstly, the acceleration along the three axes x, y, and z can be measured by the MEMS capacitive sensing unit, and the signal is fed into the ASIC circuitry. The ASIC circuitry consists of a voltage buffer for impedance matching, demodulator for carrier signal remover, and a multiplexer for multiple inputs to single output. The resulted signal is then fed into other signal processing units like the amplifier, which is there for signal boosting, ADC, the analog to digital conversion, filter chains for mode selections. Finally, the embedded functions and the control logic units can be enabled by the user with pre-programming, the smart functions. The final sensor data from the output registers can be accessed through an I2C or SPI digital communication interface using the host processor. In this slide, let's see how a MEMS accelerometer works. As we discussed earlier in the previous slides, the MEMS accelerometer is a micro machine structure built on top of a silicon wafer. The structure consists of a fixed plates, also known as anchors, suspended proof of mass, also known as movable plates, and a polysilicon spring that allows the structure to deflect when an acceleration is applied along the X, Y, or Z axis. As a result of the deflection due to acceleration, the capacitance between the fixed plates and the movable plates attached to the suspended structure changes. The change in capacitance is proportional to the acceleration along that axis. The sensor processes this change in capacitance and converts it into an analog output voltage. Next, we move on to the concepts of gyroscopes. So the first thing that comes into our mind is, what are gyroscopes and what can it actually measure? While accelerometers measure the linear acceleration, gyroscopes measure angular rotation and orientation of an object. Gyroscopes also add an additional dimension to the information provided by the accelerometer by tracking the rotation or twist of an object. As we discussed earlier, accelerometer and gyroscope together are considered as a 6-axis IMU sensor, which is nothing but an electronic device that measures a body's specific gravitational force, angular rate, and orientation. To accomplish this, gyroscopes actually measure an imaginary force that is generated due to Coriolis effect. In this slide, we can see the basic block diagram of a MEMS capacitive-based gyroscope that can actually measure the rotation of an object along all the three axes, that is X, Y, and Z. We can see that the system consists of a pair of capacitors for each given axis, and this is followed by a multiplexer, ASIC circuitry, signal processing unit, similar to the accelerometer's block diagram discussed before. The gyroscope sensor is integrated with an internal temperature sensor in the MEMS die for self-test functionality purposes to regulate any temperature-related sensitivity issues. The final sensor data from the output signal can be accessed through an I2C or SPI digital communication interface using the host microcontroller. Next, we move on to discuss the Coriolis principle using a conventional vibratory spring mass system. The spring mass system operates on the basis of energy transfer mechanism from driving mode to a sensing mode. The system basically consists of a proof of mass m in xy plane as shown. Kx and ky here represents the spring constant coefficients along the x and y directions respectively. Next, the x-axis represents the driving axis, y-axis represents the sensing axis, and z-axis represents the rotation axis of the system. We should also note that the x-axis is excited by a reference driving force F drive with an amplitude and frequency as excitation signal. Now let's assume a scenario where an angular rotation is also applied along the z-axis. This will result in displacement of the mass m along the x and y axis as shown. A Coriolis force appears in the drive and sense mode, that is x and y axis, given by Fcx and Fcy respectively. However, measuring the Fcy is of interest in this setup. From this configuration, we can see that acceleration applied along the driving axis, that is the x-axis, and angular rotation applied along the z-axis causes a displacement of the mass m in the sensing axis. And this is due to the imaginary Coriolis force acting on the mass m. This displacement in the sensing axis can be sensed using a capacitive sensing technique, and the displacement itself is proportional to angular rotation applied on the z-axis. In this slide, we will discuss briefly how the spring mass gyroscope concept discussed in the previous slide is implemented on a silicon wafer using MEMS micromachining. The system consists of a base silicon substrate with micromachined top pattern using advanced lithographic techniques. The system also consists of a proof of mass m placed above the silicon substrate as shown in the figure. It also has a driving and sensing electrodes and a suspension support beam with 4 supporting pillars. The driving system consists of an oscillator with fixed amplitude and frequency, typically of 1 MHz, applied along the x-axis. This makes the proof of mass m oscillates along the x-axis as an oscillator. Additionally, if we apply an angular rotation along the y-axis, either in clockwise or anti-clockwise, this will result in an imaginary Coriolis force that acts along the sensing axis, that is the z-axis. The sensing axis, which is the z-axis, detects this Coriolis force produced by the mixture of driving momentum in x-axis and external rotation in y-axis. A measure of the displacement along the sensing axis can produce the angular rotation rate applied. So what exactly is this Coriolis effect and the imaginary force that is acting upon the mass m? To understand this, the Coriolis effect states that when a mass m moves in a specific direction, let's say x-axis, with a velocity v, and an external angular rate omega applied in the y-axis, the Coriolis effect generates a force that causes the mass to move perpendicularly, that is in the z-axis. The magnitude of this displacement of the mass m in the z-axis is directly related to the angular rate that is applied in the y-axis. Now we understand the basics of Coriolis effect, and let's go one step closer to the tuning fork configuration with MEMS implementation. And we will also look into how the capacitive sensing is actually performed. Consider two masses oscillating in opposite directions, x plus and x minus, at a constant velocity v as shown in the figure. Additionally, when an angular rate is applied along the y-axis, the Coriolis effect produced by each mass will be in opposite direction, that is z plus and z minus, resulting in a change in capacitance between the two masses. By measuring this change in capacitance, the angular rate can be calculated. The change in capacitance can be measured by assuming the moving mass as the top plate and the beneath a fixed bottom plate, thus making it a parallel plate capacitance configuration, as shown in the top right of the slide. In this slide, the figure demonstrates the capacitive sensing element, that is, how the parallel plates convert motion to an electrical readout. On the left hand side, when no angular rotation is applied, the distance between the top movable plate and the bottom plate do not change, and the capacitance delta C is equal to 0. On the right hand side of the schematic, demonstrate when an angular velocity is applied and how the MEMS capacitive parallel plate setup changes the distance between the plates due to the underlying Coriolis force. We can clearly see that one mass deflects from the bottom plate, that is, increasing the distance between the plates and therefore decreasing capacitance, and on the other hand, a contrary effect is seen for the other mass. This difference in the capacitance is direct measure of the angular rotation applied. Now let's look into the possible operating configurations and modes of the ISDS sensor. One thing I wish to convey from this slide is that the ISDS offers great flexibility to the users in choosing the operating configurations and modes. The sensor basically works independently and in combined modes. That is, only accelerometer can be activated and the gyro in power down, or gyro can be activated and driving the accelerometer into power down mode. Or both the sensors can be activated with independent ODRs, output data rates. Such a flexibility is possible when the user can customize for their own requirements and power management, especially for industrial IoT applications. Similarly, when it comes to the operating modes, we have 4 different modes as shown in the slide. Power down, which is completely off, low power, normal, and high power modes. So in this slide, we'll be discussing about the power consumption and the noise density. The idea is to convey to you all that even if the user chooses high performance mode in combo mode, that is both gyro and accelerometer active, with a given specific ODR, the current consumption is very low. I would say this is a great takeaway point from this slide, since this actually indeed opens doors for a wide range of IoT applications and especially for industrial environments, where power management, sensor fusion, and power consumption is quite critical. Next, when it comes to the noise density for a given test conditions for both accelerometer and gyroscope, as shown in the right table, we can clearly see that the noise density is extremely low, even under extreme test conditions. Let's say example 16G here. This is an important parameter to be considered, since we don't wish to have noise signal gets higher and fades the real sensing signal to be measured. So let's have a deeper look at the specifications of the ISDS sensor. It's a very tiny compact sensor with the dimensions of 2.5 mm by 3.0 mm by 0.86 mm. It comes in a land grid array LGA package with 14 pins, with a full scale reading FSR for acceleration up to plus or minus 16 G and for gyroscopes up to plus or minus 2000 dps. It also comes with a 16-bit resolution for both accelerometer and gyroscope, and also even for the temperature sensor. The user can choose a wide range of current consumption modes, that is low, normal, or high. And even in high power mode of operation, the consumption is just around 690 microamps, perfectly suited for most of the industrial IoT applications. Next, the ODR rates are very high and can go up to 6.6 kHz with a bandwidth for acceleration around 1400 Hz and 937 Hz for gyro. Finally, the sensor is stable for a wide range of operations, temperature operations, that is between minus 40 degrees to up to plus 85 degrees. Now let's see some of the features of the ISDS sensor. User selectable operating modes, high, normal, or low. Large FIFO of 4 kilobytes. 2 interrupt pins for smart functions. Both I2C and SPI digital communication. And inbuilt embedded smart functions. Finally, let's see the possible few applications. These are not limited. The sensor is aimed for Industry 4.0 applications and IoT applications in mind. Low G static acceleration applications like platform and antenna stabilization, localization and navigation purposes, especially for tools and equipment in a warehouse. Logistics like mobile robots and AGVs. Finally, all moving objects like robotic arms, drones, and automation equipment. In this slide, we will see why the ISDS sensor is a suitable candidate for industrial IoT applications. Firstly, the sensor is very small in dimension and therefore it's easy for integration. Next, the ISDS offers a wide range of operating modes, that is the combo, only gyro or only accelerometer, hence a greater flexibility to the customer. ISDS offers one of the best FIFO buffers with 4 kilobytes of data storage. Thus, less intervention of the microprocessor, resulting in low power consumption. Next, ISDS offers I2C serial communication protocol, so it can be interfaced with RF modules. Then finally, ISDS offers 2 interrupt pins for notifications or triggering an event. This allows the user to access the wide range of embedded functions. So now let's have a look at the inbuilt embedded function ISDS offers. The active-inactive recognition function allows reducing system power consumption and developing new smart applications for the user. When the active-inactive recognition function is activated, the ISDS device is able to automatically reduce the accelerometer sampling rate and only increase the accelerometer's ODR and bandwidth as soon as the wake-up event is detected. With this feature, the system may be efficiently switched from low power consumption to full performance and vice versa. Next, we move on to the next embedded feature, which is a free fall. The free fall detection refers to a recognizing when the device is in free fall, that is, the acceleration measured along all the 3 axes x, y, and z goes to 0. In a real-life case, a free fall zone is defined around the 0G level, where all the accelerations are small enough to generate the interrupt signal. The threshold parameters defines the amplitude of the G, and the duration parameter defines the minimum duration of the free fall interrupt event. Then we move on to the next feature, which is the sleep wake-up feature. The wake-up feature can be implemented by using either accelerometer slope filter or high-pass digital filter. The wake-up interrupt signal is generated if certain number of consecutive filtered data exceeds the configured threshold set by the user. So the next embedded function I would like to discuss is a 6D and 4D orientation. Our ISDS offer the 6D smart embedded functions. So 6 orientations of the device in a space can be detected. The interrupt signal is activated when the device switches from one orientation to the other orientation. Here the 6D interrupt is generated when 2 consecutive samples only on one axis exceeds a selected threshold set by the user, and the acceleration values measured from the other 2 axes are lower than the threshold set by the user. The 4D direction function is a subset of the 6D function, especially for mobile applications. The Z-axis position detection is disabled in 4D mode, therefore reducing orientation recognition to first 4 cases shown in the slide. So the next embedded function I would like to discuss is the relative tilt. In ISDS, the tilt function allows detecting when an activity change occurs. In this slide, the tilt detection interrupt signal is enabled when the device orientation from the start position 0 is rotated by an angle greater than 35 degrees from the start position. After the first tilt detection interrupt signal is generated, the new start position, let's say the start position number 1, corresponds to the position where the previous interrupt was generated, that is final position 0. And the next interrupt signal will only be generated as soon as the device is tilted by an angle greater than 35 degrees. The next important feature of the ISDS sensor is the FIFO buffer. ISDS offer first in, first out, also known as FIFO buffer. The presence of FIFO allows consistent power saving for the overall system or the application under use, since the microprocessor does not need to continuously pull data from the sensor, but it can wake up only when needed and burst the significant data out from the FIFO. Up to 4 kilobytes can be stored in the FIFO. And the next, ISDS offers wide range of buffer modes. For example, the user can consider a FIFO mode if the end aim is to reduce the power consumption. Whereas in bypass mode, no data will be fed into the buffer and the data is bypassed to the data registers directly. Next, if one chooses the continuous mode, one can replace the old data with the new incoming data. And then bypass to continuous mode is a mode where data starts buffering after an event is triggered. And finally, continuous to FIFO mode is where stores the information about an event that has already occurred. In this slide, we will see some of the possible applications of our ISDS sensor for industrial market applications. To start with, the 6-axis IMU sensors are used in bridges, buildings, skyscrapers, cranes, and in construction industries. In HVAC, moving parts and systems. Can also be mounted on earth movers, parts and cranes. Rotation and factory equipment parts. Elevators and escalators. Pick and place machines. Industrial and commercial robots. Modern warehouse logistics like AGVs, logistic belts, and mobile robots, and also for predictive and timely condition monitoring. So to conclude this presentation, our new WSEN-ISDS 6-axis IMU sensor is a MEMS-based capacitive element with excellent technical specs like higher resolution, smart FIFO, higher bandwidths, higher ODR rates, and full-scale reading for both accelerometer and gyroscopes. It is very well suited for industrial IoT applications where high mechanical shocks, harsh operation conditions, along with low power consumption capabilities, with a larger FIFO buffer for sensor fusion and IoT connected devices. Finally, Wurth Elektronik provides an unmatchable service and support to their customers in accelerating their product to market prototyping by providing the software development kits, evaluation boards, and application notes. So before wrapping up today's webinar, I would like to quickly go through some of the frequently asked questions from our customers. The first question is, do we have SDK files available in the GitHub? The answer is yes. The users can find the standard C drives and some examples of the ISDS device on the vISO's GitHub repository. The next question is, how is the accelerometer sensitivity measured? Well, it's quite straightforward, I would say. The accelerometer sensitivity value is measured by giving a known stimulus, let's say around 1G, to the device, and then basically rotating up and down the device, and finally then subtracting the offset. What is the purpose of the internal temperature sensor? The main purpose of this internal temperature sensor is to compensate for any kind of temperature drift in other sensors like the gyro and the accelerometer. So it's like an internal offset calibration. In such cases, as we know that absolute accuracy is not so critical, and only stability and resolution is important. The main difference between ISDS and ITDS accelerometer. From spec point of view, the full scale reading is like plus or minus 16G for both ITDS and ISDS, whereas the ODRs are higher for ISDS of around up to 6.6 kilohertz, and for ITDS it's up to 1600 hertz. I would say this is the main difference. Is the aging of the sensors taken into account? Yes, for our internal qualification and quality testing purpose, we have performed some accelerated performance tests for more than 1,000 hours on selected quantity of samples, where we have performed a high temperature operating life, HTOL, temperature humidity bias, and other tests like unbiased temperature humidity tests. Yeah.
At Wurth Elektronik, we've got a fantastic lineup of sensors, including temperature, humidity, acceleration, 6-axis IMU, absolute, and differential pressure sensors. And for any questions, our live chat team is ready to assist you. Simply click the chat icon and get your answers you need. You're listening to Wurth Elektronik's What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Elektronik technical specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Elektronik's What's Up podcast.